We use that for water-based solutions, and if we have the hydroxide or hydronium ion concentration of anything, we can use it to find the other one. So this equation here that's in the box is going to be our working definition. We're going to use it a lot. If we know one, either hydronium or hydroxide, we can use this equation to find the other one. And this is given in your reference tables. Now again, ionization of water does increase as temperature increases. So that number was at 25 degrees C, which is room temperature for chemistry. So here's how we're going to use this. Hydronium ion concentration of a solution is 2.5 times 10 to the negative 6. What's the hydroxide ion concentration? Because these words are very, very similar, we tend to read them very fast. Hydronium, H3O+, is what we have here, and we're looking for hydroxide ion concentration. The easiest way to go between these two is using this equation right here. So that's what we're going to do. I'm going to take this equation and I'm going to solve it for hydroxide. So if I want hydroxide ion concentration to be by itself, I have to divide both sides by the hydronium ion concentration. So it ends up being hydroxide ion concentration is equal to 1 times 10 to the negative 14 molarity squared. Now that squared is just for the molarity. It does not go with the number, just the units. And then I'm going to divide that by my hydronium ion concentration. Now, I'm just going to plug these in, or the number in that they gave us in the problem. They gave us our hydronium ion concentration, so that's just going to go in right here. So it's going to be 1 times 10 to the negative 14 molarity squared divided by that 2.5 times 10 to the negative 6 molar. When you divide those, you find that your hydroxide ion concentration is 4.0. We want to deal with 2 sig figs since that was given in the problem, times 10 to the negative 9. Molarity cancels with one of these, so I'm just still left with molarity, and that makes sense because if it's square brackets equals, the units are in molarity. So that's just a really quick way to work with this equation and go from hydronium to hydroxide or hydroxide to hydronium. It's always 1 times 10 to the negative 14 divided by the one they give you in the problem will give you the one that you're looking for. All right. The next thing we'll have to do is talk about classify this solution as neutral, acidic, or basic. So if our hydronium concentration is equal to our hydroxide concentration, that means our acid stuff is equal to our base stuff, then we end up with a neutral solution. If our hydronium ion concentration is bigger than my hydroxide ion concentration, I have more acid stuff than base stuff, then it is acidic. And if my hydroxide ion concentration is greater than my hydronium ion concentration, my base stuff is greater than my acid stuff, the solution then is basic. So if we look back at the problem that we just worked, and this is our hydronium ion concentration, and this is our hydroxide ion concentration. We're going to compare these two numbers to decide whether the solution is acidic, basic, or neutral. Now you want to pay attention to these exponents because here's where it gets a little tricky. Remember, times 10 to a negative number means we have to move, this is a tiny number, and we got to move the decimal 9 places in that direction. So that's going to make that a very small number. And it's going to end up, our hydroxide is smaller than this number right here for hydronium because this decimal only has to be moved 6 places. So our hydronium ion concentration is greater than my hydroxide ion concentration because 2.5 times 10 to the negative 6 is greater than 4 times 10 to the negative 9. So the solution is acidic.